Hey everyone, my name's Brian Campbell and I'm a NASA Senior Earth Science Specialist at the NASA Goddard Space Flight Center's Wallops Flight Facility in Wallops Island, Virginia. I'm also the ICESat-2, the Ice Cloud and Land Elevation Satellite 2 Mission Education Lead. So today I'm going to talk to you all about ICESat-2 and show you some of the cool things that ICESat-2 has been able to measure in its first 3 years of operation. Here we have a really cool ICESat-2 3D printed model. ICESat-2 has been in space for 3 years, just over 3 years now, and has seen some amazing things. What I'm going to show you first is how to build and describe all about an ICESat-2 micro environment. And this is just something you can create using stuff around your house or at your local craft store inexpensively. And it's to showcase the different things that ICESat-2 can measure, like bodies of water, ice, tree height, land, and clouds. So it's pretty cool. So I hope you'll be excited about it. And then I'm going to show you some really cool things of how you can go on the NSIDC, the National Snow and Ice Data Center's online tool called Open Altimetry to look at ICESat-2 data from your area or all over the world. I hope you enjoy. Thanks so much. Here's a snapshot of the ICESat-2 microenvironment. Here's what you need to create your own ICESat-2 microenvironment. You will need a clear plastic container. You will need a cotton puff or cotton balls, a small piece of wood, a small plastic container which you will freeze, a water pitcher, a green laser pointer or green laser pen, dental floss and tape, small model trees like ones you'd find in a train yard setup, toy polar bears or penguins, whichever you prefer, and water for plastic containers. Now that you've seen the snapshot and the items that you need to create your own ICESat-2 microenvironment, I'm going to show you a time lapse of how to build the ICESat-2 microenvironment, and then we'll go to the next step and talk to you about all the things that make up the microenvironment. Basically, things that ICESat-2 can measure from space. All right, everyone. So now you know basically how to build the ICESat-2 microenvironment. And here we have it again, okay? And once again, we have the ice, which this is representing some sea ice. We have the land. We have some trees. We have some clouds. And of course, since we're in the Arctic, we have some polar bears. The purpose of this is to showcase, what the ICESat-2 satellite can measure from space. So as the ICESat-2 satellite is traveling above the Earth in a near polar orbit, basically 88 degrees north, 80 degrees south around North and South Pole. It's sending off laser photons, okay? So it's firing off laser photons like this 10,000 times per second, okay? And I'll teach you more about that later on in the presentation. But what I wanted to show you here with this ICESat-2 microenvironment is basically showing you the things that ICESat-2 measures, and then we're going to use the laser to showcase exactly, what the laser does and what we've been able to measure with ICESat-2. So I'm going to fire it down onto this environment, okay? Because you can see, the water is very clear, okay, very pristine. So the laser pulses actually go through the water surface, hit the bottom, and back to the top, and back to the satellite. We've seen ICESat-2 measure bathymetry in areas where the water is very clear and very still. So this is representative of that. And as you know, when laser or light hits a white surface like ice and snow, okay, it has a high albedo, basically the reflectivity, the ability to reflect light. So we have this high albedo, so you can see it's reflecting pretty good. It's absorbing a little bit, into the layers of the ice. But what's going to happen here is ICESat-2 will bounce the laser photons off the surface of the ice, okay, whether it's sea ice or land ice like the ice sheets in Greenland or Antarctica. But what it does is it bounces it off, and we calculate the time it takes the laser pulses to leave the satellite, okay, and bounce off the object on Earth and come back to the satellite. With that information, we can figure out how tall things are, the height of things are on our planet. So we have the ice, we have the water, we also have trees, okay? Trees have height. There are over 3.03 billion trees, trillion trees on our planet right now. And obviously, ICESat-2 won't measure all of them, okay? Citizen scientists and researchers won't measure all of them, but we're making a huge dent in measuring these. But you can see here, a lot of this light, you can actually see the photon hitting it, okay? And it happens the same way. We calculate the time it takes laser pulses to leave ICESat-2, hit the top of the tree, and then go back to the satellite again. And we can calculate how tall those trees are. Now, one of the pretty crazy obstacles here with ICESat-2 are clouds. As you can see here, the clouds really absorb the light, okay? And a lot of the light does not penetrate through the clouds into the surface of the water or to the trees, okay? Or to the ice. That's a problem. And there's been lots of algorithms written to combat that issue. So, but that's one thing that ICESat-2, really doesn't like a lot of clouds. Really thick clouds are bad. Cirrus clouds are bad because they're made of ice crystals, and that light, those photon light gets scattered. So this is, once again, a simple thing to make, okay? A simple thing to make, with household items or items at your local craft store. But it would be cool for classrooms or just to show people a little bit about the environment that ICESat-2 can measure. And this is the ICESat-2 microenvironment. Hello, everyone. My name is Brian Campbell, and I'm a NASA Senior Earth Science Specialist and ICESat-2 Mission Education Lead based at the NASA Goddard Space Flight Center's Wallops Flight Facility in Wallops Island, Virginia. Today, I'm going to talk to you about the Ice Cloud and Land Elevation Satellite 2, or ICESat-2. I'm also going to show you some really cool things, including a demonstration of how you can create an ICESat-2 observation microenvironment using just common things you can find around the house or at your local store. And then also, I'm going to show you some really cool facts about ICESat-2, some of the observations that have been taken across the planet, and also how you can look at elevation and height data for everything from ice to bodies of water to tree canopies using the Open Altimetry Online Tool. So at NASA, we have a huge operating and future science fleet. And I'm going to draw your attention to the Earth, where you see the International Space Station orbiting. What I have here is I have a circle around the ICESat-2 mission. ICESat-2 is a mission that's near and dear to my heart because I have been working on the mission since the beginning of the thought process with ICESat-2. I actually worked on the original ICESat satellite, which flew from 2003 to 2009, and it was decommissioned in 2010. But as you can see here on this graphic, there are lots of Earth-observing missions around our planet, including instruments on the International Space Station that are there and will soon be launched to the space station. ICESat-2 is just an amazing piece of technological advancement, and I'm going to show you why in the next few slides. So ICESat-2 was launched September 15th, 2018 from the Vandenberg Air Force Base, which is now the Vandenberg Space Force Base in Lompoc, California on California's central coast, aboard the last Delta II rocket. Now, ICESat-2 is just a very... So, here are some of the objectives of ICESat-2. Measuring melting ice sheets and investigate how this affects sea level rise. Measure and investigate changes in the mass of ice sheets and glaciers. Estimate and study sea ice thickness. And measure the height of vegetation in forests and other ecosystems worldwide. This is a lot going on with this mission, but we have had some amazing results in the last 3 years. So, here are a couple cool facts about ICESat-2, and that was a pun totally intended. The Atlas instrument fires 10,000 laser pulses per second. Each laser pulse contains approximately 300 trillion photons. The ICESat-2 satellite flies in a near-polar orbit, basically 88 degrees, at 15,660 miles per hour, which converts to 25,202 kilometers per hour, at an altitude of 310 miles above the Earth's surface, which converts to 498 kilometers above the Earth's surface. And spectacularly, on November 1st, 2021, the ICESat-2 satellite's Atlas instrument fired its 1 trillionth laser pulse. That is amazing. So the ICESat-2 satellite uses a technology called LiDAR, which you may have heard of. It stands for Light Detection and Ranging. LiDAR is an active remote sensing technology, basically the laser version of radar, which uses pulses of laser light to measure the 3D structure and height of objects on Earth. These measurements are made on Earth's surface between 88 degrees north and 88 degrees south, hence the near polar orbit. And you can see here, there are a couple images here on the bottom center and the bottom right. This is showing you when the Atlas, the Advanced Topographic Laser Altimeter System instrument on board ICESat-2, was being built at the NASA Goddard Space Flight Center's clean room. It's an amazing bit of technology, the amount of work that went into this to be able to fire 10,000 laser pulses per second and be able to collect all this data back to the satellite is just a feat of technology that, I've been at NASA for just about 21 years now, and this still amazes me that this has been built and has been functioning so well. We know at NASA we have very, very smart people doing amazing things, and this still blows my mind. So with ICESat-2, you can see here, this is a post we created for ICESat-2 just to showcase exactly what ICESat-2 can measure. And you can see it can measure buildings and apparently Ferris wheels in cities or in, at carnivals. It can measure the ice, the height of ice sheets and sea ice. It can look at mountains. It can actually measure the height of clouds in the atmosphere. It can also measure trees and vegetation, the tree canopy especially, and these bodies of water like rivers and streams and oceans. So it's be able to look at sea height, and which is a huge thing for ICESat-2, because since ICESat-2 is also measuring how much land ice or ice sheet ice is melting, that plays an effect on global sea level rise. So ICESat-2 is able to measure how much ice is melting from Greenland and Antarctica, but it can also measure how the height of the oceans are changing. So now, let's take a look at some of the amazing features on Earth that ICESat-2 has observed with its laser altimeter, that being Atlas. Some of these graphics are just amazing. So first we have one for off the Bahamas. This was on October 26, 2018. What you're seeing here is, on this graph is in the green, these are the ATL03 photons, so the Atlas photons, and you're looking at the ATL8, the SSH, that's that sea surface height. So what you're seeing here in the green, you're seeing all these photons that were fired down by ICESat-2. But what's amazingly cool about this is you can see that blue line that's running through the middle where it turns green with the photons. That is the sea surface. But you notice all of those photons underneath that sea surface, and you can see some type of, terrain under there. That is underwater bathymetry. So in the Bahamas, the water is very clear and still where ICESat-2 hit this area. So it was so still and clear that the laser photons from ICESat-2 penetrated the water surface and bounced all the way through the water and bounced off the bathymetry, the features at the bottom of the ocean, and was able to map out this underwater bathymetry. So isn't that amazing? Here we have Crater Lake National Park. And you can see here on the right side, this is showing you where the path of ICESat-2 has crossed. And what you're seeing on the left side is the graph of showing the photons and what it mapped out. As you can see here at Crater, you can see that it's going up on the left side as in an elevation, and you can actually see some tree heights here. These are tree canopy heights. You see those spikes on that slope. And then all of a sudden you see the crater, okay? You see the body of water, and you can see how it mapped out that flat surface and some bathymetry in that still water. And then you see the edge of that lake, then the slope moving to the right side of the graph, along with some more tree canopy heights as well. Here we have Lake Ontario. I really like this one because you can see the contrast between the land surface and the water. And you can see that this is relatively flat in the surface of this water. So it runs from this kind of, cliff side on the left side of this graph all the way through the water. And you can see a lot of those photons, the ATL03 photons, have passed through this water and then return to the satellite. And then you can see, once again, you can see some trees and tree canopies on both sides of this, on the top of that cliff side, and then on the slope exiting out of the water in basically the southern portion. One of my favorites and a place my family and I visited this past summer in July and August is Sequoia National Park. This is amazing because you can see the mountainous terrain here, as well as many, many of the tree canopies that were able to be mapped out by ICESat-2. And a lot of these are these giant sequoias that are part. And you can also see these valleys and ravines that are part of Sequoia that you may have seen if you visited this area in person. It's a sight to behold. Here we have another place that my family and I visited on the same trip. We have Yosemite Valley from October 15th of 2018. And you can see how this valley is structured based upon the elevation we get back, and you can see lots of tree canopy and how the photons are returning back to the satellite. So on this map, you can see the photons in green. In orange, you can see the terrain elevation coming back from the ICESat-2 satellite, and then the ATL8 tree canopy height in Yosemite. Now, what I'm going to do is I'm going to shift a little bit, and I'm going to go on to the Open Altimetry site, which is a research website to visualize ICESat-2 height data through its orbits. It was created by and managed by the National Snow and Ice Data Center in Boulder, Colorado, that houses the ICESat-2 data when it's processed from the satellite observations. So we're going to take a look at Open Altimetry, and we're just kind of randomly going to move around the planet and zoom into different ICESat-2 orbits, just so you can see exactly, the possibilities here. And then also, I'm just going to plug in a latitude and longitude to show you that if you have an area that you really want to study and see if ICESat-2 hit that location, you can then plug in that latitude and longitude, or you can even do like a latitude longitude boundaries look up, and you can see if ICESat-2 hit the areas that you may be studying or interested in. If you might have gone out and taken observations of, snow, ice, tree heights, building heights, things like that. So, let's jump into that for a few minutes. All right, let's take a look at the Open Altimetry page.
As you can see, it's openaltimetry.org for org. And when you go on, you can see that there are two options. There are browse ICESat data, that's the original ICESat satellite, and then browse ICESat-2 data. We are going to choose the red one that says browse ICESat-2 data. So all you have to do is click on it, and what's going to happen is a map is going to render. And what you'll see here are all these green ICESat-2 orbit paths, and the green dots you see, those are the ICESat-2 photons that were sent out by Atlas, the Atlas instrument, the Advanced Topographic Laser Altimeter System. And those were then collected back to the satellite. They bounced off the surface of the Earth or an object on the Earth and came back to the satellite. So now what you see here is a quick little tour. You have the plus and minus here on the left. These are zoom in, zoom out. You have this, the percentage is how far you're zoomed out or zoomed in. We have drag and zoom, where you can just move around. Here we have the coordinates that you can enter. We'll go back to that in a second. You can filter by specific beams. We're not going to worry about that. But what I really want to draw your attention to here is the calendar. And what you're seeing here is the most recent date of ICESat-2 data, because there is some data latency, and because it takes a while for the data to be processed because of simply the volume of data that comes in at about a terabyte of data a day. But the latest date you see here is Thursday, July 15th. And as you go through the year, this will change. When we first started getting data back, the data latency was a little longer, but then we've streamlined the process to get the data processed. And, therefore we can get the data out faster. So, there won't be real-time data with ICESat-2 because of the data latency and the processing, but the data here is great. So let's take a look. First off, I'm just going to zoom in, randomly. Let's just go to, let's say, the Amazon rainforest. So you can click the screen to zoom in, or you can just, use, the cursor and use the plus. But what I'm going to do is I'm going to zoom in, and what you're going to see here is you're going to see all these red lines appear. These are also ICESat-2 orbits. These are past orbits. The green ones you saw were the most recent orbits. These are past ones. You can see there's a lot of them. So let me show you a real cool trick on what you can do here. So I'm going to zoom in just as far as I can go. So I'm going to go all the way. Actually, no, I'm not going to go all the way in. I'm going to go to where I see just one or two of the red orbit paths. As you can see here, I'm going to center this, and one of these orbit paths looks like it runs through agricultural land in South America, as well as some forested area. So what I'm going to do is I'm just going to put the cursor over the line, over the orbit, and just click. And what's going to happen is it'll show you the ID number of the orbit track for ICESat-2 and a drop-down menu of the dates that ICESat-2 was nearby. So I should also mention that this track that you're seeing here is 11/8/2018, but all these other dates are ones that were nearby when ICESat-2 was east or west close by of this first orbit path right here. So if I go and I click on, for instance, the next date, 2/7/2019, okay, what you get here is, and I'm going to exit out of that, and what you get here is you get all these colored dots. These are the photons like you saw earlier with the open altimetry information I was showing you. But what you can do here is if you want to see what the elevation is and what the tree canopy heights are for this location, let's zoom in as far as we can, and actually we can go in a little further. All right, actually I'm going to go out a little bit, and this is what you're going to do. You can play around with this. It's a lot of fun. So I'm going to just stay right here so we get some agricultural area and we get some forested area. So up here in the top left on the open altimetry, the word open altimetry, we see select a region. I'm going to click on that. And when you do, you get this crosshatch, this plus sign. And by holding the mouse down, you can draw a box over these photons. And check this out. This is really cool. So once you get the box where you want and the photons that you want it to cover, just let the mouse go. And then you will get a box, a dialog box pop up. View elevation profile, view signal photons, or close it. We're going to go to view elevation profile. So what's going to happen is another screen, basically a browser tab will open up. And what you get here is you get two graphs. The first graph is showing you ATL08 ground elevation and canopy surface. So what you're seeing here is for each one of the photons that was measured, you can see these red photons, basically the strong beam, and the weak beam, which are some of the green ones that are still there. But what you're seeing here are the surface elevations that correspond to what you see here. Okay? So I should also mention that what you see, these photons that you see, you might not see them in a consistent path. You'll see that there's a bunch of breaks here with this green, with the green photons here, these green colored photons. There may have been a cloud in the sky at this time, which didn't allow the laser pulses, the photons, to hit the surface and return back to the satellite. But let's go back to the graphs. What we really want to focus on here are the canopy heights. So those trees that you see, so corresponding to these photons that you see, okay, these 1, 2, 3, 4, 5, 6 photons that you see in this forested area, these are the 6 photons and where they're corresponding. And when you scroll over this, what you're getting is the canopy heights. So remember, these canopy heights are an average of all the trees that were part of this 13-meter diameter footprint. So this dot here, this photon, is a 13-meter diameter footprint on the ground. So the number that you see here, for instance, this 20.25386 meters, what you're seeing here, this canopy height represents an average of all the trees within that 13-meter diameter space. So you can see, if you want to know the tree heights for those areas, we have 20.25, 22.81, a little lower 22.2. We have a pretty tall grouping of trees here, these canopies at 28.89 meters. So this is really cool that you can do this, right? So you can go and take a look, and you can align the tree canopy heights to the surface elevations for this area, for this location. As you can see, we have an elevation here. The 201.95 meters corresponds to this canopy height of 28.89 meters. So there's lots of amazing data here. I'm going to exit out of this and go back. Now, I'm going to zoom out. And what I want to show you here is we're going to go a little further north. We're going to go up to some ice. So we're going to go up to, let's go to Greenland. So let's zoom way out. All right. And then move down here to Greenland. And I'm going to zoom back in again. All right. So let's do that. All right. There we go. There we go. Let's actually go to the southern tip of Greenland. That's a cool place to be. All right. We see a lot of ice melting there. We get a lot of that ice melting data back from the original ICESat mission, as well as ICESat-2, where we see a lot of that land ice, or that ice sheet, melting and moving into the ocean, creating some of that sea level rise. So we're going to zoom in even further just so we can, kind of isolate some of these orbit paths. All right, we're going to go right here. So let's do it this way. Zoom in a little more. We'll go back down to that southern tip. And you can see some of these have crossed here, but we're just going to grab, so we can get some ice and maybe some body of water. So let's do this one here. We're going to click on this one here. Okay. So here we get November 2nd of 2018. So let's just randomly go and let's say we want to know 1/30/2020. So we'll click on that. Let's see if anything comes up. There we go. So let's go to this one here, the green and orange. Now, I should mention that when ICESat-2 fires these photons, these laser pulses from the satellite, what happens is it basically, the photons get split into basically 3 pairs of photons. So what happens here is, as ICESat-2 is calculating the height of objects on Earth, because of how these photon pairs are spread out, these orbit paths are spread out, we can calculate the slope of the ground on the surface underneath ICESat-2 at the same time. ICESat-1 wasn't able to do that because it was a single laser pulse, a single laser beam hitting the planet. It didn't have these 3 beam pairs, which that is another reason why ICESat-2 is so technologically advanced, versus a lot of other satellites out there. So let's zoom in a little bit, and let's do the same thing here with the select a region. So we're gonna select a region, and I'm just gonna grab some of these here. I'm gonna do this and all the way over the body of water, okay? So we have some land surface, some barren land area. We have a little bit of potentially ice and snow, and we have a body of water. So I'm gonna let go of that. View elevation profile. All right, here we go. Here we have the ATL08 ground elevation canopy surface. Now you see this flat area here, okay? This corresponds to when ICESat-2 went off the coast here through this body of water. This is where you see this flat surface. And then over here where you see it jumping up here, this little peak here and this little peak here, that is when it hits the land surface again right here, okay? So you're seeing that flat body of water area there. And then also all of this up here where it gets super high and the elevation gets pretty tall, that is where it's on the land surface. So it's crossing over some mountainous area in Greenland before it hits the coast. So we can also look at Canopy Heights. So it apparently, in these areas where you see the green, there are actually canopies where you can get tree canopies at the southern tip of Greenland. So isn't that amazing stuff? So what you're seeing here is you're seeing different ground elevations. You're seeing the elevations over the ice, which is super important to help understand how that elevation is changing, meaning how that ice is melting, how fast it's melting, where it's melting. And we can do this all over the planet, especially though on the ice sheets of Greenland and Antarctica. And then we can also look at the sea ice over the Arctic and surrounding the Antarctic Peninsula. So that's pretty amazing stuff. And you can see apparently there are a lot of tree canopy heights in this area. So all of these here, this really concentrated bit of tree canopy heights, that corresponds to this area up here, this area on the land surface prior to the satellite hitting the open body of water. So that's really amazing stuff. All right. So lastly, what I want to show you here, I'm going to go back and I'm going to click on this coordinate. All right. Now, since the fall 2021 AGU is being held in New Orleans, Louisiana this year, let me just plug in a latitude and longitude of New Orleans. So here we have the longitude. So we will pop this in minus 90.0715, and we'll do a latitude of 29.9511. And then we hit update map. All right. So now you'll see, I'm going to zoom out just so you can see that where we are. All right. You can see that it's centered New Orleans and those coordinates in the middle of the map. And if you zoom in, and if you happen to get off, out of New Orleans, see we kind of landed in the water there, we can hit update map, and that'll center that coordinate back into the middle. So let's zoom out a little bit again to isolate a few of those orbits. All right, here's one right here. So I'm just going to pull it over to the center, and I'm going to click on it. Now, you can see here we're in a very, highly urban area with lots of houses and streets, and you see trees and rivers. So you see lots of really cool things in this image. So we're going to click on this again like we did before, and we're just going to randomly go to, let's say, Happy New Year 2021. So 1/1/2021. So let's just click on that. And, oh, you see one pops up over here. So let's scroll over here. And this is really cool because it looks like it is moving over a bunch of things. So let's zoom in a little further, just so we can get that river. And too bad it didn't hit one of those boats here. That would have been really cool. So let's zoom in a little bit more. Okay, how about that? So we should probably get some really cool Canopy Heights here as well. But I'm going to just kind of center that, and I'm going to hit this select a region again. And I'm going to pick a bunch of these photons. I'm going to go all the way up here to just near these, looks like these baseball fields. And I'm going to go across the water. All right, and I'm going to let it go. And we're going to view elevation profile once again. Check this out. Look at all these cool things you see. You see this change in surface elevation. So this could be corresponding to maybe buildings in this location. All right. You see the elevation change pretty dramatically, and then it dropped. But what you see here in this flat portion here with these yellow photons, this corresponds to these yellow photons over the river. Okay, see that? That's really cool, isn't it? So you can see that here. And apparently, this looks like pretty murky water, and I think it is usually. So it's pretty, it's not clear. So we won't get really bathymetry data from that because it's so cloudy. You have to have the really clear waters like you saw earlier in the Bahamas video. So let's scroll back down again. Well, there you go. There's lots of tree canopies here as well. So that, you can see that corresponds to all of this area up here where you see it running through the neighborhoods and hitting trees, places like that. So there must have been a bunch of trees here that the ICESat-2 photons from the Atlas instrument have hit. So once again, you can align the surface elevations to the canopy heights if appropriate. So I just wanted to show you just a couple cool things. My suggestion is go and explore this, or, go out in your local environment and find where you'd like to know the height of something, and then go and see if ICESat-2 has measured it. And then if you want to look at trees, you can use that NASA Globe Observer Trees tool to measure the tree height and then compare that to ICESat-2. But what I want to say is have fun with this. Check it out. It's a really cool tool, and you can do lots of things in it, and it's just fun to explore areas that you may have been to, areas that you're researching. So enjoy this, and check it out. And I want to thank the ICESat-2 mission and the National Snow and Ice Data Center for their Open Altimetry Online Tool product. Thanks so much.
Now, since I just showed you the Open Altimetry page, we have some really cool cross-program collaborations of data analysis and citizen science that's related to ICESat-2, the GLOBE program, and we have an extended activity with the Open Altimetry page you just learned a little bit about. So let's talk a little bit about what the GLOBE program is and why and what it has to do with the ICESat-2 mission. So GLOBE stands for Global Learning and Observations to Benefit the Environment. The GLOBE program is an international science and education program that provides students and the public worldwide, including citizen scientists, with the opportunity to participate in data collection and the scientific process. Basically, we have over 50 measurement protocols where students, educators, citizen scientists, and researchers alike can take observations in their local environment to help better understand our changing planet. And these observations are everything from surface temperature to soil moisture to biometry, tree height, to vegetation, to precipitation, and everything in between, even looking at the phenological reproduction of seaweed. So very, very diverse group of measurement observations that you can do for the GLOBE program, what helps us build a robust data set for helping us understand what's going on our planet. As you can see here, though, we have a little graphic here, GLOBE by the numbers. Currently, GLOBE is being used and data is being collected in 126 of our planet's countries. We have over 37,000 schools, over 42,000 teachers, over 213,000 GLOBE observers, and these are people who use what's called the NASA GLOBE Observer, which is the GLOBE program's citizen science project. Now, you see this number for measurements, almost 210 million measurements? That is because the GLOBE program, with its 50 or so measurement protocols, has been in operation since it was created by Al Gore in 1995. It was released on Earth Day, April 22nd, 1995. So since then, we have had almost 210 million points of data put into the GLOBE database that anyone can access for research purposes. And then also, just this month, we're closing in on 1.5 million measurements in the GLOBE database. And what's cool about the GLOBE program is that this program is funded by NASA, and there is support from NOAA, NSF, and the U.S. Department of State. Now, I mentioned the NASA GLOBE Observer, okay? NASA GLOBE Observer is a program where citizen scientists can use their mobile device to take observations and submit them to the GLOBE database. Now, currently, we have 4 protocols that can be done. You can do cloud observations, mosquito habitat observations, land cover observations, and tree heights / tree circumference observations. What I'm showing you here is I'm showing you promotional material for the idea of taking these measurements. And the ultimate goal here is to have citizen scientists take observations of tree height using the NASA GLOBE Observer Trees tool for citizen science, and then potentially compare them to the tree canopy height coming from the ICESat-2 satellite. And it's very easy to do. And what's really cool about this is that when you do these comparisons, you can use that tool that I mentioned, the Open Altimetry tool. But with this, we have it basically set up that your mobile device and the app work together. The app uses the phone's built-in magnetometer to measure the angles to the base of the tree and to the top of the tree using your mobile device's camera. And then there is also another calculation where basically the app figures out your stride length and your eye level based upon the height that you input into the app. And then it also calculates the distance where you're taking the observation of a tree as you walk to the base of the tree, counting your steps. And however many steps you count, a calculation is performed based on that step count and your estimated stride to figure out what the height of the tree is that you're observing. Now, with this, here we have where we can compare the ICESat-2 and GLOBE program data. First of all, there's different ways we can do this. We can take observations using the NASA GLOBE Observer, take tree height observations, and then go into the Open Altimetry page and see if ICESat-2 has measured that tree or other trees in that location. I happen to be able to measure a Bradford pear tree in my neighborhood in Maryland. It's an isolated tree, meaning that there are no other trees around it, and it happened to fall within the ICESat-2 Photon Footprint. Basically, what this ICESat-2 Photon Footprint is once the laser pulse leaves the satellite and the photons hit the planet, they hit the planet and create about a 13-meter diameter footprint. So, for instance, if there are 20 trees that fall within that 13-meter diameter footprint photon, the height that's going to be returned from ICESat-2 will be the average height of all the trees it was able to measure. Now for this, ICESat-2 happened to send these photons down, and one of them hit just this tree. So what I did was I went out and took an observation, and I got a tree height observation, and I then looked at ICESat-2, and I did a comparison of that as well. And I noticed that when I went out and did my first tree height observation for this Bradford pair, we had a tree height of about 19.41 meters that I got using the NASA Globe Observer Citizen Science Apps Trees tool. ICESat-2 measured the tree at 19.13 meters, so that is extremely, extremely close. Very close. But then what happened was we went to measure it again, and we measured it again because in August of 2020, we had Tropical Storm Isaias hit our area in Maryland with lots of wind damage, and actually it snapped off half of the tree. Half of this Bradford pear tree was destroyed. And I went out and took another NASA Globe Observer observation, and the tree was about 16.61 meters tall now. So it lost about 3 meters of height. Now, what I'm hoping is, and it hasn't happened yet, is that ICESat-2 will fly back over and a photon will hit this location. Now, even though ICESat-2 may fly over this same tree, if there is too much cloud cover in the sky, and as you saw with that little demo that I showed you what clouds can do to the lasers, okay, it still may not measure it, but I'm keeping my fingers crossed because I'd like to see how close to the 16.61 meters ICESat-2 can measure that tree at. So, just an event like Tropical Storm Isaias shows you that you can, really see a change in tree height. Now, also for an area near my neighborhood, actually this one is in my neighborhood, for a group of trees. So what I did was I went out and took observations in a wooded area on my property. I took tree height observations of many trees that fall within the 13-meter diameter footprint that ICESat-2 dropped on this location. And the average of all these I got for the NASA Globe Observer was 18.93 meters. ICESat-2 found it at 19.66 meters. So once again, that is extremely close. So once again, I have here over on the right, you can go and look at this data to see if yours matches up with ICESat-2, or just to see if ICESat-2 hits your area. Then you can go out and take observations. But you can check it out at openaltimetry.org. And finally, here are some great links for you to take a look at. We have the ICESat-2 Mission website, ICESat-2 on Open Altimetry, the Globe Program's landing page, the NASA Globe Observer Trees tool, ICESat-2 Photon Fridays featured video, which after this great links page, I'm going to end everything with this really cool video of basically in Germany, it's an old airport hangar, okay? And it was turned into a water park. And one of our ICESat-2 scientists, Dr. Kelly Brunt, was reviewing the data and noticed that the ICESat-2 photons were able to measure the bathymetry at the bottom of a pool in this water park inside this hangar in Germany. So it's absolutely amazing, and I hope you enjoy it. And then we have a lot of great visual resources on the NASA Goddard Scientific Visualization Studio about ICESat-2. Feel free to contact me at any time if you have any questions about the ICESat-2 mission, the Globe program, the Globe program's NASA Globe Observer Citizen Science Tool at brian.a.campbell@nasa.gov. Thank you and enjoy the rest of the Fall 2021 American Geophysical Union Conference. Bye-bye.
ICESat-2 science team had a group meeting, of course virtually in this weird era that we're in. And to make the meeting a little bit more interesting, our science team lead, Lori Magruder, she sort of challenged all the participants to find what's the most interesting thing that you've seen inside the ICESat